So I didn't know where to focus this talk. I wasn't given, I was given a lot of freedom, I'll put it that way. And having spoken with a number of students and postdocs who went to the first session last month, part one, I got the feeling that I could do something that was more detailed, more applied, and that it might work well. So I'm hoping that that direction is going to work. I won't be talking about my research today. I do auditory neuroscience. I especially study the cocktail party problem. And for more information on my research, please visit my website. But I'm going to be talking about signal processing today. And I'm going to talk about this from the point of view of someone who needs signal processing, acquires physiological data, uses Fourier transforms and filters all the time, but doesn't really know that much about them aside from you need this kind of filter here or you need that kind of filter there. Or more likely, it's not that you need it, it's that the last postdoc in the lab used this filter here, and the last grad student used that filter there, and so that's what you do because it works. So I'm going to be talking about some fundamentals. I'll be talking always in the context of physiological signals, MEG, EEG, ECOG. And I will try very hard not to use too much math. I'm trying very hard to use picture examples whenever I can. I spent the entire train ride here this morning trying to clean up equations and replace them with MATLAB generated figures as illustrative examples instead. So hopefully that will work. I've never given this talk before. It was constructed completely from scratch over the last week, so I apologize if there are rough spots along the way. The talk will basically be broken up into what the Fourier transform does and what it can't do for you. Filters, what they do, and I think importantly how they do it, because most people don't see how filters work. They just see what the end result is for their particular data. A section on what choices you have when choosing a filter and why you should make, what you should consider when making decisions. And then if there's time at the end, I've got a grab bag of special topics, including causal versus non-causal filters, windowing, and low-passing envelopes. And I encourage questions at any time along the way, in part because this is like one of the classes that I teach, which is signal processing and data analysis for grad students in cognitive neuroscience, but also because I'm not quite sure what I've skipped and when, so if you can point that out to me, I would be grateful. So first, Fourier transform. This will be the most complicated set of equations that you'll see. The Fourier transform says, it's a mathematical statement, that every time domain signal x of t, and I'm talking only about discrete or acquired signals here, can be re-expressed as a bunch of sinusoids, each with their own coefficient. It's important for us, especially in this talk, that everything has been discretized, that everything has a delta t, a sampling frequency, a finite duration of time. And so the time steps are incremented by integers time delta t. And also the frequency steps. You have finite frequency resolution delta f, go up the same amount. When you take the Fourier transform, if you start off with endpoints, you end up with endpoints. And there's a specific relationship, it's a reciprocal relationship between the time resolution and not the time resolution with the frequency resolution, but the time resolution with the sampling frequency. So the sort of the highest frequency goes along with the time resolution. And conjugate to that, the highest time, the duration of the signal, goes along with the frequency, with the frequency resolution. So I'm going to try and stay away from equations and give some examples instead. So here's a typical signal that you might want to take the Fourier transform. It's supposed to look like something that you might be looking for in MEG or EEG data. In this particular example, I have a delta t of 10 milliseconds, in case that helps you get a feeling for what's going on. And this signal is 500 milliseconds in duration. And you can take the Fourier transform of that. And that'll give you the coefficients as a function of frequency. And in particular, this delta t of 10 milliseconds corresponds to the sampling frequency of 100 hertz. So in the frequency domain, I will go up only to half the sampling frequency, because everything else above that is redundant in some sense. This duration of 500 milliseconds will become our frequency resolution of 2 hertz, and so that's the spacing here. If you want better frequency resolution than 2 hertz, you had better change the duration of your signal. So these two are linked, delta t and sampling frequency, and these two are linked, the total duration and your frequency resolution. And if you want to change these things, as I said, for instance, in this case, I'm looking at a similar kind of data. I've got an extra pair, I've got a pair of these bumps, so now I've got a longer duration. I'm keeping the same sampling frequency, so I'm keeping the same time resolution. But since I've doubled the duration, then I have halved the frequency resolution. And so you can see there are many more frequencies in here. If you're used to doing this on a computer, for instance, I'll talk about MATLAB again a lot, not because I recommend MATLAB. It's got its pros and cons, but because it's very useful and it's the one I use. You typically won't see this going on. You won't see the number of frequency slots doubling because it will just scale everything. But I particularly like this because you really should, if you're doubling the time, double the length of this. And if you're doubling the time, you should keep the same frequency span here. You should just have more points. So when you do these kinds of manipulations, try to keep these things in mind. Even though MATLAB or most computer programs will just expand everything to automatically fit the screen, that may not be the best way to see what's going on. OK, so why do we care about the Fourier transform? Well, we may be measuring several different kinds of signals from different sources. This one in red, if you look at the Fourier transform, is mostly in the 10 hertz region, although it's pretty broad. This one in the blue is higher frequency, mostly in the 20 hertz. And these would presumably come from different sources. These are all synthesized, so they don't actually exist anywhere, except on my computer in MATLAB. But when you measure them, you'll measure something that's the sum of them both. And so we don't actually see any of these. We see what the sum is. But what we'd like to do is to be able to distinguish, say, we know that this is related to our particular study, and we know that this is not. This makes this our signal, and this our noise. Someone from a lab across the hall might view it the other way around. So we want to be able to separate them, perhaps to concentrate on one, perhaps to concentrate on both. And this is what we measure. So again, this is the same thing that we measure. This is the Fourier components of the things that we're trying to measure and we're trying to separate out. And you can see in this representation of it that there's a lot of overlap. These are linear superpositions that we're measuring with MEG or EEG. And so in this frequency region in particular, although anywhere where one of them is not zero, what we measure is going to be the linear sum of two different sources. And separating linear sums is notoriously difficult. If I ask you to take the number 7 and figure out which two integers added together to give that number 7, it's going to be hard. You might say 3 and 4. You might say 0 and 7. But this is really, in some sense, our job here. Our job is to, because we only have this, but we're looking for this, to do the best we can, whatever the best means. And so this is our goal, to try and go from this to these two. And what we can do is we can use a filter. So despite, yes? I'm only plotting the magnitude. I'm giving complete short shrift to the phase today. Yeah, so it's good to clarify that. I had actually, in my description of this presentation, I had mentioned phase, and I had thought I was going to spend a lot of time on it, but I think that'll have to be part 2 for some other day. So phase will appear here every now and then, but mostly it will be inferred. And this actually pains me because I think phase is much more interesting than magnitude. So the way that we break up in practice a mixed signal that comes from different frequency bands is not by looking at the Fourier transform and divvying it up. That turns out to be a very bad way of doing things that introduces all kinds of artifacts. The way that has the time-proven way of doing this is by applying a filter. And so, for instance, if we apply to our measured signal a specific filter, we can get that output from the filter, and we can compare that to the actual source and see that they're pretty good. This filter did a good job. The filter cannot do a perfect job because there's been information that's lost by this linear mixing, but we can do okay. And similarly, if you're trying to get the other signal, the blue signal out, you can use a filter, and you can get something that's not so bad out of it also. You can look at the spectra of the 2 different ones, and you'll see that there are some differences. There's certain differences in phase as well, but only the magnitude ones are plotted here. But to some extent, those differences don't matter so much, because if you're interested in what's going on in time, you can make some changes in what's going on in frequency, and as long as those changes aren't too important, then you can get what you're looking for out, or something close to what you're looking for. All right, so let's talk about these filters that accomplish this. They're certainly not magic. Just to get this out of the way, because I won't spend much time talking about this, broadly speaking, we talk about filters because they're frequency selective. So for instance, you might use a low-pass filter on your data if you're looking at evoked potentials. You might have a cutoff at 40 hertz or below because you know that's where the signals are. And from your perspective, everything above here is noise, and so you want to attenuate it. If it's low pass, pass means that it's 1, it lets things through near 100% in the low frequencies. You could also call it a high stop filter, but we don't do that for traditional reasons. But it really is a low pass, high stop filter. Band pass filters, you might be interested, for instance, in the theta range between 4 and 8. This nice band pass filter would let you concentrate on that. There's all kinds of noise issues that at low frequencies. You might want a nice high pass filter to get rid of your 1 hertz and keep everything from 2 hertz and up. Band stop filters are not so common. You might want to get rid of your alpha. If you're not doing an experiment on alpha, it may be just large and annoying, and so you might want to get rid of it from that perspective. You also may want a notch filter. You probably have some 60 hertz noise. Notch filters are a lot like band stop filters, but they're extremely narrow. So much more important than that is you know more or less what kind of low pass, high pass, band pass filter, because you know where your frequencies of interest are. You know what you want to keep. You know what you want to get rid of. Much more interesting and more difficult, the kind of thing that I want to approach today, is how selective should these filters be? So this is called an ideal filter. It's a rectangular filter in a rectangular shape in the Fourier domain. Ideal is a terrible name for this filter. It implies that this would be really, really good to use. It's not. It's ideal in that it's a mathematical ideal, but as far as a useful filter, it's got terrible, terrible properties. Do not ever use an ideal filter. Do not even try to construct one if you could. And in particular, don't try to construct things that look exactly between 8 and 12 hertz and look nothing on either side. However, you might want something like that. You might want a filter that has a relatively sharp transition. Turns out that there are some real problems associated with very sharp transitions that are some of the reasons why you wouldn't want to try to use an ideal filter. They are useful depending on what you need, but you may also want a much softer transition, and I'll be talking a lot about why you would want one versus the other. All right, should have just used these. Don't use ideal filters. Sharp transitions are okay, but beware. Soft transitions are very useful. Okay, so how do the filters work? Filters work. These are all linear filters or linear time invariant filters. They take linear combinations of an input signal. For instance, x of t here represents your input. And linear combinations of the input and earlier versions of the input. So here we have the signal x of t, and here we have the same signal but delayed. The signal is somewhat in the past. And this filter is made by taking the signal now, the signal in the past, and adding them together, averaging them. Or another way of looking at it is for any given moment, for instance now, the output of your filter will be an average of what the input is now plus what it just was. You might have, this is a much more advanced kind of filter. We'll be talking about these also. It might take the signal that you're using as your input and then combine it not with an earlier version of the signal, but an earlier version of the output that you just had. So this is a system or a filter with feedback. Because you have feedback, then it's in some cases much, much more efficient. You're not dealing only with things going on right now, but you're also dealing with things that you've already processed, and so it can help you out. And then, so this turns out to be, it happens to be a low-pass filter. This happens to be a high-pass filter. And this one, which is a mix of both, it's got present and past for the input. It's also got past to the output. This happens to be a notch filter. All right, so let's take a look at, as an example of how filters work, this 2-point moving average filter. It's always taking the average of 2 points, and it's moving along in time. Just by the fact that this is taking a local average, we expect that it will do certain things for us. We expect that it will smooth out some rough spots, because averaging smooths out roughness. If you have a sudden change, this filter will take whatever that sudden change is, and it will modify it so that it was a little bit like before the change. Or if you go one time to the future, then it'll also do that. So these sudden changes will be softened by this 2-point moving average. We expect specifically that if a signal is not changing much at all, that taking the local average won't do much at all. So, signals that are changing slowly won't be affected much. And you might guess from some of these expectations about smoothing over and soften changes that this might be a low-pass filter. A low-pass filter meaning it lets through things that are slow and it attenuates things that are moving fast. You won't have to guess that. We're going to see what happens. So let's take as an example a particular signal so we can see what's going on. I constructed this signal to have a couple of different kinds of properties. And the way we're going to see how this filter works for this particular signal is we're going to also use the delayed version of this same signal. So we'll take this signal and duplicate it and then move it backwards in time. Change its color so that we know which is which. And then put the two on top of each other so we can see what this filter is doing on this specific signal. We can just add them, add the red and the blue, and we'll get a new signal, this black signal. So the blue is the input and the black is the output. And we can see that there are not too many changes, but there are some quite dramatic changes if you look carefully. And I want to see step by step how some of these are made. So in particular, if we look at, we said for slowly changing parts or parts that are not changing, we expect them to not change at all. So recall what we're doing here is we're just adding the red and the blue for each given time. And so if we look at what happens when we add a bunch of zeros, then they stay a bunch of zeros, not too surprising. Similarly, if we add a bunch of ones, they stay a bunch of ones. A bunch of negative ones, stay a bunch of negative ones. So we can see that it's true, that slowly changing signals stay not changing. Let's look at some other features, some other places. This is an interesting time point because there was a sudden change. And so if you look at the actual signal blue, it's a 1, but the delayed signal hasn't caught up with it yet, so it's a 0. If we add them together, we get a half. Now that's just 1 point. If we expand our viewpoint a little bit, we see that this sudden change from 0 to 1 has now become a more gradual change. It stops at a half along the way. Similarly, if we're going all the way in one quick step from +1 down to -1, then we now take a stop at 0 along the way. So fast changes are becoming softer. Similarly, if we're going up, and if we look at this region, we can see that this is moving relatively slowly. It's not like going up and then coming down right away. And what's happening is that it's not changing that much. There is a slight change, though, in terms of the time. It's a little bit subtle and hard to see. But as you can see here, because this blue and red are different, and this blue and red are different, then the values that you get are moving the rise of the sinusoid, the sinusoidal part, a little bit to the right. So it's slightly delaying the sinusoid as it goes through. So we can talk about those expectations. We can see what we've actually seen. Sudden changes are softened. Slowly varying signals are largely unchanged. And there is a slight delay, whether it's the sinusoidal component or whether it's the rise time from going 0 to 1. We have not addressed yet whether this is a low-pass filter, but we will get there. And the way we'll get there is to go back to the Fourier transform. And so here's a signal. It looks a lot like the one I gave before. We've got a different time duration here. It's much shorter. And so because this is only 160 milliseconds, then our frequency resolution has gotten much, much worse. It's now more than 6 hertz instead of 1 or 2 hertz. And coming back to the equations, I've grayed them out because I don't want to talk about them too much, except to say I've neglected this part of the Fourier transform. I've neglected so far that the Fourier transform re-expresses our signal as a bunch of sinusoids. And so what I'm going to do here is throw away the equation and look at this specific example, that the way that we get this signal, according to Fourier, is we take a bunch of sinusoids and we add them together, each with their own component. And you'll see, if you remember what the Fourier transform magnitude spectrum looked like from the last slide, that this is the same thing. What this represents is you take this signal and you multiply it by 5. You take this signal and you multiply it by around 8, et cetera, all the way down, sum them all together, and that's how you can reconstruct the original signal. So what we're doing when we're looking at the effective filtering on frequencies, filtering in the Fourier domain, is we're going to say we're going to filter. So this just says the same thing. Every signal, you get a bunch of sinusoids. It's Fourier coefficients. Just to bring phase into it, because I still feel terrible at neglecting it, you'll notice that these may all have different phases. So these phases were actually all correct for the previous one. When you multiply them by the Fourier coefficients, then what you really want to do is these Fourier coefficients may also affect the phase. So if we're really careful, we'll mention that. If we're just giving a tutorial for today, we can neglect that to a large extent. Getting back to filter, when we're filtering our signal and we care about what's going on in the Fourier domain, we can break this up into just filtering the sinusoids because the Fourier coefficients are just numbers. If you filter a number, nothing happens. It remains the same number. It's filtering the signals that's going to tell us what's going on. So if we want to see what's going on in terms of what kind of filter this is, whether it's bandpass, low pass, we want to see what it does to these Fourier sinusoids. And somehow it's going to add up to this, because we know that that's true. And the way it does it is each one of these is filtered. So each one of these components, you can do what we did before. We can take it, we can add its time-delayed version to itself, and then come up with what it looks like over here. And what you can see is, ignore the first point for the moment. That'll come back later to haunt us, but for now we can ignore it. You can see that these sinusoids come back relatively intact. These sinusoids get squashed. And if we look at that as a trend, we can see how much they're being maintained or how much they're being squashed. And this tells us the magnitude of the filter in the Fourier domain as a function of frequency. So this says that this particular filter is a low-pass filter because it lets low frequencies in. It squashes the high frequencies. But more importantly, the way it works is not just some magic or something that is unknowable or even not worth knowing. The way it works is really very simple. It's just taking the signal and, in this case, averaging it with the low version itself. This can be done for other kinds of filters. So this is another nice one. This one, instead of averaging, this does a local difference. We expect that this filter, as I said, will exaggerate differences. Whenever there's a difference, it will show up. Therefore, whenever a signal is varying, then it will amplify that because it will look for differences. At the same time, if a signal is slowly moving or slowly changing, then that difference is going to be small. And so it's going to attenuate the sections of the signal that are slowly varying. And for all of these reasons, you might guess this is going to be a high-pass filter. And we'll do the same thing. We'll take the signal, a delayed version of itself. In this case, we'll subtract instead of add. And get, in this case, a very different version of the output, because adding and subtracting are very different operations. And just to go through some of the same mechanisms that we went before, we're going to be comparing the blue version with the red version, which is delayed, and now we're going to be subtracting instead of adding. The simplest places to look at first are the pieces that are changing very slowly. So for instance, here it's changing slowly, and the output also changes slowly. But it doesn't have to be 0, even if it's changing slowly at some other value, because that's looking at local differences. That still comes out at 0. So whenever things are not changing, it replaces it with a 0. It doesn't replace it with the same thing unchanged. Doesn't matter whether it's positive or negative, or 0 somewhere else. At the same place we saw before, we can see that we're subtracting the 2. So this 1 minus a 0 becomes a half. But the difference from before is that now we're in the plus version, in the moving average, it went from 0 to a half up to 1. Now, because it's not changing over here and not changing over here, it goes up to 1, but then it goes back down to 0. Similarly, we've got this big negative change, 1 to minus 1. That gives us a big negative signal, positive. If we look at the sinusoidal portion again, now we can see that there is a pretty visually dramatic change, which is that it still looks sinusoidal, but it's much, much smaller than it was before. OK, so what have we seen? The differences are exaggerated. The quickly varying aspects of the signal have been amplified. The slowly varying aspects have been attenuated. We don't know, strictly speaking, whether or not it's a high-pass filter. So we'll do the same thing we did before. And see that for each of these signals, when the signal is changing not at all or very slowly, then not much of the signal comes out. But when the signal is changing quickly, then because it's changing quickly, it's got a lot of differences in it. And those differences are occurring fast, and so those differences pop out over here also. We can look at the magnitude of each of these as they come out, and we can say, yes, this is a high-pass filter. So again, it's not that the important thing that this is an example of a high-pass filter, and you should know what a high-pass filter is. It's that you can see the actual mechanism, that you're just taking the signals and adding them and subtracting them to the same to themselves delayed to get these different filters. Here's one where this is a filter with feedback. So it's using the passed version of the output, not the input. And in this case, for the low speed sinusoids, the ones that are not varying very fast, then not much comes out at all. It's only at the very end, when they're really moving, that you get substantial output. And so this ends up being a very strong, very high region, high-pass filter. All right, so you've seen some filters and how they work. Now, why are there so many filters? I mean, we're not going to use the ones that I've just given as examples because they're too simple, they're too simplistic. Why are there so many different kinds? What do those different kinds represent? And which filter should I use? So most of the rest of this talk is going to be on these kinds of decisions. Good. How selective should these filters be in the sense of should the frequency transitions be sharp versus soft? One of the big questions is always going to be, should your filters be only feed-forward or should they include feedback? Where the feed-forward only filters are called FIR filters, the feedback filters are called IIR filters. What kind of order should I use? Does it matter whether I use an order of 4 or 140? The answer is yes, but maybe not in the way that you think. Should our filters be causal or non-causal? This is supposed to be one of those questions that's so easy that there's an obvious answer, but it turns out to be one of those things where it looks like that the correct answer, the obvious answer is too easy, so that must be wrong. But then when you look at that answer, it turns out that that one's not right either, and so you have to go back to the original answer. So I will talk about why not to use zero-phase filters. And then other questions like if you're going to use an FIR filter, what kind? If you're going to use an IR filter, what kind? Okay, things to keep in mind in all of this is that it's by design that filters modify the signals. When we come in to a lab and we see this incredibly dirty signal and we want to clean it up using a filter, our first instinct is to say, I want a filter to not modify my signal because I want the clean part, and the clean part is in there. But that's not how filters work. Filters have to modify the signal. They work by taking the signal and messing it up with other versions of itself. So just keep that in mind. They are going to be changed. Fortunately for rationality, most decisions involving filters involve looking at a trade-off. If you change things too much one way, you get one effect. You change things too much the other way, you get a different effect. These trade-offs are typically valid, and you have to decide how far along the trade-off spectrum you want to make your decision. You go on one side, there's good things and bad things. You go on the other side, there's bad things and good things. It's important not to go overboard one way or the other. One of the things that I see with grad students and postdocs, because this is how we think, is that we want to do things right. And when you see that there's something good, you want to do that good thing the best you can. And so you learn that there's some feature that you want, and you make that feature the best possible thing. Don't do that. There's almost always a trade-off. You may be looking at your signal in some version that makes it look absolutely beautiful. But when you look at it in a different way, it's really, really ugly. So keep in mind that no one likes to make compromises, but you have to make compromises here. At the same time, there are some decisions that do allow you to avoid artifacts without any repercussions, and so we want to know what those are, so we can just make those decisions without having to think too much about them. All right, so the first question we'll address is, what about this, the frequency transitions? What does that do? How does that help us? How does it hurt us if we make one decision or another? Time and frequency are inextricably linked. You cannot change the time, in this case, the frequency content of a signal without changing the temporal content of the signal also. That's just how the mathematics of the Fourier transform of how frequency works. As simple examples, if you have a low-pass filter, it's going to lengthen the changes. You might have very, very fast, beautiful transitions, a very narrow peak, and you might like to keep that peak. But if you use a low-pass filter to get rid of your high-frequency noise, then you're going to take that peak and you're going to make it a little bit longer, because that's how low-pass filters work. Similarly, high-pass filters, if you've got a nice DC response that changes to another nice DC response, if you high-pass it, it's all going to bring them all down to 0. So you may not want to high-pass it if you really want those things, but if you're high-passing it because you have no choice, for instance, you're doing EEG and you've just got this drift going on, then you may just have to sacrifice certain things, but that falls into the compromise region. A specific example that we're going to look at is the sharper frequency transitions. So this is something in the frequency domain. They produce something in the time domain, which is an artificial elongation of the signal. It makes it last longer, and it's called ringing. So here's a good example of ringing. This is the neural response that you're hoping to see, because this is what the brain is producing. This is what you actually measure, because when you measure things, they're not so nice. This actually, for anyone who records these kinds of experiments, this will really look beautiful. I mean, this, if you're used to this is garbage. But this is a really clean version of the signal. So this is probably after some processing has been done. So let's focus on that, because we're not going to actually ever see the underlying neural response all by itself. This is the response spectrum, or the spectrum of the Fourier transform of this measured signal. And we could see, I apologize that these numbers are so small. I noticed this too late, and I didn't want to spend the entire train ride going back and regenerating all my figures to make bigger numbers. But you can take my word for it, if you can't see it, that this is 10 hertz here. And so since all of this stuff here looks like high-frequency garbage, then one thing that you can do, and one thing that we typically do if we're looking for evoked responses, is we make a low-pass filter to get rid of all of this stuff, which is a lot of this stuff. So let's look at what different kinds of low-pass filters would do for us. Here's a filter with a beautifully elegant sharp frequency transition. We can see that at 10 hertz, there's not much going on. So just removing everything above 10 hertz, keeping everything below, should be nice. It should be nice. Here's one with a soft frequency transition. This one doesn't look so nice, because it's allowing a lot of this crap to remain in our signal. It's not being very aggressive in removing stuff that we know is not important. What happens when we use these filters? Well, if we use the filter with a sharp frequency transition, it turns out that that sharpness has this pretty nasty side effect. This is what ringing looks like. Ringing is named after what happens when you take a tuning fork and you bang it. After you've given it the impulse, it still keeps ringing afterwards for a long time. That's what this is. And if you're looking to analyze this signal, which has a really nice positive peak with a certain width at this time, and it's got a really nice negative peak, which is much narrower right afterwards, and then some noise. And in many cases, in evoked response analysis, you care how big those peaks are, how wide they are, when they occur. This is terrible. First of all, this has given you a whole bunch of other peaks. That's bad, because if you see a peak, you think that the brain is doing something there. Second of all, the relative height of these peaks has been changed. It's really enlarging this negative peak or this trough over here. And it's also changing the width so that all of these oscillations tend to have about the same relative width. So it's turning something very real here into something that is pretty artificial. And if you saw this, you would be tempted to start analyzing these things, and that would be bad. Whereas if you use this ugly, soft frequency transition that leaves lots of noise in, it really does a pretty good job. It's got some bumps over here, but let's be honest, our signal's got some bumps over there too. You can't expect to get rid of all noise and keep only signal. There's going to be some compromises. What's also nice is that we've got the relative peak sizes correct. We've got the relative peak widths correct. So this is a case where the soft frequency transition, leaving some of the noise in, is much better than harshly removing everything you consider to be bad and just assuming that because it's such a beautiful looking filter that it will do the right thing. A little more about ringing. I never want to say never use a sharp frequency transition, because sometimes you do need it. Sometimes there's a very tight boundary between a frequency that you want and a frequency that is absolutely terrible to keep in your analysis. So in those cases, you're going to need the sharp frequency. I'll do the example of a notch filter. And in that case, there is going to be ringing, and that's all there is. You need a very sharp filter if you're going to get rid of your line noise, your 60 hertz noise or 50 hertz noise. And if you see ringing around 60 hertz, then you'll know what it came from. So here's an example notch filter. I'm assuming that in as many cases that the 60 hertz noise has already been taken out by some hardware filter, but that doesn't mean that you don't have 180 hertz still lurking around. And the way I'm going to see what's going on here is I'll use a very non-neural signal. I'll use an FM sweep. So this is a sweep that it's a pure tone, but it starts off around 50 hertz, grows linearly to about 500 hertz, and then goes back down to about 50 hertz. And so what should happen is that when the signal gets up to about 180 hertz, then that part of the signal should be removed, and every other part of the signal should look fine. So it should look like the same lambda here, but with a little bit removed here. Now, in practice, spectrograms are not so good. If we want good temporal detail, we're not going to have good spectral detail, and I'm using this as a temporal example. So it turns out we're not going to actually see that little gap. But what we are going to see is ringing. Because what happens is the frequency is exactly at 180 hertz when you get to that time in your FM sweep, are attenuated, but the frequency is on either side where they're not so attenuated, but there's very, very sharp frequency transitions. That's going to cause ringing, and you can see that here. So ringing is narrow band. It occurs at the frequency where the sharp transition is, and it's extended in time. In practice, notch filters won't show you ringing because of the reasons that we use notch filters. We use notch filters specifically for very steady sources of noise. And the ringing is going to occur when you bang the tuning fork. And so if you're already if you already have 180 hertz line noise or 60 hertz line noise, then you're not going to get ringing. You're just going to keep on getting those things that are there. So notch filters in practice will not give you ringing for the kinds of signals you put into them that we care about. But if you put in a signal that really did not have 180 hertz and then it had it and then it didn't, then you would get the ringing, and it's unavoidable because you need the notch filter. So this is an example of compromises. You want to avoid sharp frequency transitions when you can. If you can't, then go ahead and use them, but be aware that you could get ringing from them. And at the same time, don't go all the other way. Don't go, OK, I'm only going to use really soft transitions. Because let's say you're interested in alpha activity. Then you're interested in the 8 to 12 hertz here. It's OK to have some 4 and 8 and some 12 to 16. But you may not want to go all the way down towards the delta region. Because then you're going to start looking at other neural sources, other neural networks that are giving responses that are not what you are interested in. So soften your stance a little bit, but don't go all mushy either. Feed-forward versus feedback filters. FIR, which stands for finite impulse response, is feed-forward only. IIR, so feed-forward only. Examples are moving average, like we saw the 2-point moving average. I'm assuming that many of the filters that researchers here apply come from a button that you press in a piece of software that says you want this kind of filter or that kind of filter. Avoid moving averages in general as an FIR filter, because they just have really terrible spectral properties. They look nice and pretty because it's like, oh, I'll just take 4 neighbors or 5 neighbors and average them together. Turns out those are not so good. What you really want is a weighted moving average. You want something that, as you go out further and further away, you get less and less coming into the average. If you have a choice of a Parks-McClellan filter, which is sometimes called an optimal filter, then that's a nice one to use. They might ask you some other questions along the way, but it is a good one. IR filters, these are the ones with feedback. Because it has feedback, then instability is an issue. If I were to have feedback now talking, it would be because the sound coming out of the speakers is going back into the microphone and then coming out. And if that feedback were to be positive, then that would be bad. That would mean that the system was unstable. That doesn't usually happen, but it's something to watch out for. IR examples that you may have heard of are Butterworth filters, which are not awful, but they're not great. Everyone uses them. Chebyshev filters and elliptic filters. Elliptic filters are really very good and very powerful. They require a little bit of extra effort to use, but I do recommend them. And we'll get there. How do you choose which is which one to use? There's no universal answer, so I'm going to give you some guidelines. The things you're going to use to figure out which one to use are the group delay of the filter, which is when you put a signal through a filter, there's something intrinsic about the filter that causes it to be delayed. That's called the group delay. A related but not quite the same issue is filter startup. When you first turn on the filter for data that you have acquired starting at some time and you don't know what happened to the data before that, there are some initial condition issues. Stability if it's an IIR filter. And I'll address the group delay issue first. So again, filtering changes signals by design. It's part of what the filtering does. All filters, if they're doing anything frequency related, will also change temporal features of the signal. And if the filter is causal, meaning that nothing happens in the output until something happens in the input, then that's always going to incur some delay. Because for the output to be fully formed, it has to use the input now and the input before and the input before. And so by waiting all that time for all the different delayed versions, then the output will reflect a delayed version of the input. Just looking at this filter we've seen before, this is the 2-point moving average. You can see what happens to this relatively slow-moving sinusoid the peak and the trough of the input, in some sense, disappear, but in some sense get sort of lost in the space between the time points. When you have a discrete signal, there's nothing between the samples. It looks like there's something in this picture, but there's nothing there in your computer. They're in memory locations that are right next to each other. But it looks like, on the whole, this 0 would have been here, if there is one. It looks like that there is a delay, a group delay is often called tau d, of about half a sample. And if we look at a much faster sinusoid, bing, 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 then the same thing is happening. This peak gets rounded off. This 0 falls between a positive and a negative. And it's also about half a delay, half a time step. If we look at, this is a weighted 3-point moving average, but the same idea, we can see in this case that this peak is shifted by a whole time step. This 0 is shifted by a whole time step. If we look at the higher frequency component also, it's being attenuated, but a peak still remains a peak, a trough still remains a trough, but now it's sent over by a full time step. And so we might guess that for this filter, that the group delay is 1 delta t instead of being a half a delta t previously. So it turns out, if you look at the theory or do a lot of numerical experiments, that you can always calculate the group delay of a filter by looking at the average delay imparted by all of the pieces of that filter. So if the filter uses now plus a time step before plus a time step before that, then the average of those 3 is 1 time step before that. And so it's, that average is going to work. And roughly speaking, if you look at the order of the filter, which is, for historical reasons, the length of the filter minus 1, then the group delay for an FIR filter can always be calculated to be half that order, and then in time times your delta t. I should also mention, just in case there are people who really do know discrete filtering or real DSP, I'm using a more practical but not too common convention in that I keep the time. Most textbooks will just say that the group delay is this, but I think that as physiologists, then time really matters, and so I prefer to break with convention and keep it there. Because it is proportional to delta t, then, so to order, then the more complicated the filter, the higher order the filter is, the longer the group delay will be. So if you look in you ask MATLAB to find a really nice FIR filter, and it says that, sure, I can find one that does everything you want, and it's 500, it's an order 500 filter, then that's going to be a really long group delay, and you may not want that. Assuming that you can keep it down, because there is this delay aspect intrinsic to the signal, if you care about when a particular thing happens in your signal, so you want to calculate the latency of something, then you may need to compensate for this group delay. And if you're looking at a peak, then you can really just for FIR filters subtract the group delay and compensate for that peak. If it's not a peak, then it's a little trickier, because as these signals get spread out, then where the rise and where the fall are will also be spread out. And so that can be a little bit trickier. Also, and this is important for practicality, since the group delay is proportional to delta t, the smaller your delta t, the better. And what that means is if you've got raw data coming out that's sampled at a very high frequency, and the first thing you do is you reduce the sampling frequency, so you just to save disk space, for instance, to save memory, you may want to do some of these filters before you do that, because if you create an FIR filter with really, really small delta t, then your delays will be commensurately smaller. We saw what group delay looks like for this filter. for the sinusoids. You can also see it for an example signal that's not pure sinusoidal, but it's a little bit trickier because a group delay is sort of an average phenomenon. It's not an individual feature phenomenon. So for instance, this peak here gets turned into two neighboring peaks. So it's sort of spread out a little bit by half a sample. And similarly, we saw already that if it's sinusoidal, that this peak here and this zero, the actual peak gets lost in the middle, the zero gets lost. And so we can also see the half sample group delay, but it is a little trickier. IIR filters, or filters with feedback. These are a little bit nastier because the group delay is not a constant across frequencies, but actually depends on the frequency. That's not necessarily bad, but it does mean you have to be a little bit more careful. It matters what kind of filter you're looking at. So in this case, this is the group delay of a particular low-pass filter. And I'll tell you the general trend of what happens to the group delay, which is in the pass region, where the magnitude is 1, so it's letting things true, the group delay is relatively constant. You might argue that this is rising, but it's really all around 20 milliseconds, so it's relatively constant. In the transition region, where the group delay is longest, and so the worst case scenario in terms of group delay will be filters in this transition region. So you want to watch out for those, and you want to make sure that there aren't a lot of them when you're using your filter. And then finally, in the stop region, where the signal's being attenuated, it doesn't really matter. If it's a long group delay, it's short group delay, it's strictly speaking, it's theoretically possible to have a negative group delay. If it's being attenuated enough, then it doesn't matter what the group delay is. So you can not worry about it. Let's go back to looking at these frequency transitions, because the frequency transition region is where the longest group delay is. And let's look at these two different low-pass filters that are low-passing at around 10 hertz. And the group delay, OK, so I can tell you that the sharper transition, the longer the group delay. This is the one we just saw. This is the one that has a very, very sharp frequency transition. And the key thing to notice here is that we've gone from about 20 milliseconds to about 500 milliseconds because of the sharpness. So that's really terrible. And this is strongly related to the phenomenon of ringing. So if you're worried about group delay, then do not use very sharp frequency transitions. If you're calculating latencies, as you might very well be, you may want to compensate for this. If you find that the typical group delay in the pass region is about 20 milliseconds, then you can subtract about 20 milliseconds. And it's again, this is for peaks. And as long as the peaks are dominated by frequencies that are away from the transition, then that'll still be pretty good. If you get towards the transition, then you're sort of messing yourself up because you're putting the transition in your signal. And so that's, in some sense, you're doomed already from that point of view. It so happens that when you construct IIR filters, that the group delay doesn't scale with delta t. There's sort of an overall more or less cancellation. It's not exact. But that means that IR filters are fine at lower sampling frequency. All right, the next topic we have to consider is signal loss due to the filter startup. So we've already said that the output signal depends on signal values in the past. That's great. That means at the very first moment, the first part of your output signal, it relies on a part of your signal that doesn't exist, because you're looking to the past of the first data point you have. And roughly speaking, until this filter output settles down from that, then your output is really not going to be well defined. As an example of that, If you're looking at this 2-point moving difference, if 0 is where you start, then the output at 0 is given by the input at 0. That's fine. It also requires the input before 0, and we don't have that, so we don't know what this is going to be. We can assume something about it, but assuming something isn't going to really tell us that much. But if we wait one time step, if we want to look at the next value of the output, then that's equal to half the value of the input right now, and also half the value of the previous one. We have that. And from then on, you're fine. So for this filter with 2 parts, then we have startup issues for the first time step, but after that, it's fine. Roughly speaking, maybe even exactly speaking, the problem is only for n order times delta t. And so if you're using an FIR filter, what you can do as a practical point of view is just use earlier data. If you started off using only 100 milliseconds before your t equals 0, use another 100 milliseconds. And you'll just throw that part away. With FIR filters, it's not that critical because MATLAB will also just assume 0 for you. That may or may not be a good assumption, but it's what it does. If you throw out if the first 100 milliseconds of your output are unreliable, if they're crap, either because it's bad data from the beginning or because it's zeros, it doesn't matter. Just throw them away. So that's all fine. It is reason to keep the order of your filter small for FIR filters. And this is yet another reason why FIR filters work better at high sample rates, because you can throw away a lot more points for only a small amount of time. For IR filters, the problem is much more subtle. So here's an example of an IR filter. It has feedback. The output at time 0 relies on the input at time 0, which you have. It relies on the output at the earlier time, which you don't have. So you have to write this off. The output at the next time, though, relies on the input at that time. That's fine. But it also relies on the output at the previous time, which you've already written off. So that's a problem. You have to make certain assumptions if you're going to get anywhere. So what I recommend is to do what I just said earlier. Keep extra earlier data. So if you have an extra 100 milliseconds of data, put that in. It'll give the filter sort of time to settle down to what it would be. And in this case, because it depends on what the group delay is, how much you're actually going to need, put in however much you can afford. Which is to say, if you've just got a lot of stuff with nothing happening, great, use it all. If you're epoching your data and the time before this processing is actually the response to some previous stimulus, then you may not want to use that, depending. MATLAB does allow you, if you're using MATLAB, to put in these initial values that you don't actually have. And sometimes that actually helps. For instance, it'll put zeros by default, but if you know that your signal wasn't starting at 0, it was starting at some constant value, then you can precede all of that with those initial constant values, and it'll take much less time to recover from that. You may even want, if all you need is roughly generic data, you need data with the right spectrum, then you might even be able to take data from the end of your signal, put it back in the beginning, pretend it was there, and that may help the signal settle down a little bit faster. The other issue I mentioned was stability. So because IRF filters employ feedback, if the feedback is negative, that's great, but if it's positive, that would be bad. All common IR filters are designed to be stable. They're designed so that all feedback is negative. However, because of numerical round-off error, then sometimes that doesn't happen. I can tell you from theory and experience that this breakdown is more likely at higher order filters. And so I recommend, just as a generic rule, if you're using IRF filters, keep it down. An FIR filter, you might use a 100th order filter. With an IR filter, never use that. Keep it down below 10, 4, 5, 6, great. 8 might work sometimes. when I first started doing this stuff, I went into a lab where someone was saying, oh, I'm going to use a fourth order elliptic filter here. I said, why fourth order? Why not 17? And the only response I got was, 17? Never use 17. It's a stability issue. This is not really a burden because IR filters of low order tend to be more smooth. The higher order ones are more likely to have a very sharp transition. So this is, in some sense, another reason, another way of keeping your order down, your transition down. How would you even notice if you had instability in your filter? Well, let's say this is your raw signal, which we've seen before. This is a stable filter. In this case, I've chosen the one that does have ringing because the ones that are likely to become unstable are also more likely to have ringing. If I tweak it a bit, make it too high order, then I get this as the response instead. They clearly look very different, but you still want to know, since you don't have access to this, you do have access to this, but you may have forgotten it. You may just be pressing a button in your lab. How do you know that this is unstable? Well, it's not subtle, but you have to know where to look. Your raw signal was about 1. Your output of the unstable filter is about 10 to the 10. So a lot of people do not look at these numbers when they're looking at MATLAB figures because they're small, but they're really important, especially when they're 10 to the 10. OK, so how do you choose a filter? Again, these are all just guidelines. They're gentle guidelines. If you have a high sampling frequency and plenty of initial data, then consider using FIR filters. FIR filters are nice in that the group delay doesn't depend on the frequency. There are fewer things to worry about. And the main things you have to worry about are throwing away initial data, which if you have a lot of it is not a problem, or a very long group delay. But if you've got a lot of data, then a long group delay is also fine. Which FIR filter should you use? Parks-McClellan filters, if you have the choice, if you have the option, are nice. You'll be asked some questions about them, and I'll show you the kinds of questions that you're asked for elliptic filters. But you can choose them to have soft enough frequency transitions, but not too soft. This is just a little reminder. When you do choose a filter and you're writing your paper and you're putting the stuff in the methods section, please give a little bit more detail about the kind of filter that you use. I review a lot of papers where they said the signal was low-passed with a Butterworth filter, period. That doesn't help me. That doesn't tell me. Maybe it'll tell me that it was what the order was. Actually, I'm usually not told what the order is. I'm usually told what the cutoff is, but even then, not so much. Please, if you put any work into choosing your filter, then please report what it is, so that we know that when we see something as a reviewer or a reader, that it's not an artifact, that it's really something from the brain. FIR filters, there's a lot of them, and they're of varying quality. If you're just pressing a button on your software package, take a little bit of care. Maybe they're good, maybe they're not. To some extent, it depends on the kind of signal processing knowledge the software author knows when writing the package, and that's an unknown. So if it's not high sampling frequency with not lots of initial data, you'll probably want to use an IR filter because that's the other kind. If you just need to choose a filter and you don't know what it is and you don't care, you just need a low pass, Butterworths are fine. If you really don't know what's going on, use a fourth order Butterworth, and that's the end of it. And just report that that's what you're using. That's what I use when I need a quick and dirty something. I need to low pass my data. I don't care what it is. I just need to see it low passed. If you do care, then you should really consider using an elliptic filter. You have a lot more control. If you really care about your alpha leaking into your theta leaking into your alpha or your delta, then you may want to use an elliptic filter. Again, report all of this information in your methods section. IIR filters are less prone to variability. There's a small number of families of IR filters, so you don't have to worry so much about that in your software package. The way to use an elliptic filter is it needs 2 bits of extra information aside from where you want the transition region to be. And these are called tolerances, but they're really just slop factors. One of them is in the pass frequency band, so where the signals are passed, it's supposed to be 1. Well, how careful are you about that 1? For instance, it probably doesn't have to be 100%. Maybe if you're 1% off, that's fine. You would never be able to tell that in your data. And so put that number in, say 1% error is fine because I know my sources of error are greater than 1%. If you're using MATLAB, it happens to require this in dB. 1% is about 0.1 dB in this case. The other thing you need to know is the tolerance in the stop band. You don't need it to go all the way to 0. You just need it to get small. Maybe down by a factor of 100 will be perfectly fine for you. And in that case, if you did then MATLAB, you would say you need 40 dB attenuation, and that's fine. A decibel, sorry. All right, so that was a very, very fast transition, and I should have low passed it. So roughly speaking, to give some closure for the choosing the filter, FIRs are really probably best and easiest for raw unepoch data. And for everything else, you can try using an FIR, and maybe you'll have an initial data, and maybe it'll be great, and that's wonderful. But you may have to use an IR data, or you may like IR filters for some other reason, and that's also fine. Now that you know a little bit about what to look for in IR filters when they go wrong, and to make sure that they're not doing it to your data. All right. Causal and non-causal filters. I cannot remember what the next slide is. Okay, good. All the filters we've been looking at are causal. They take things from the past to figure out what's going to happen now. They don't go into the future to figure out what's going to happen now. All of these filters have effects, therefore, that trail off into the past. Depending on the length of your filter and the order of your filter, then it may propagate backwards to the past. Some of these changes are desirable, like low passing, smooth transitions. Some are undesirable, like ringing. But they're all to the past. They're all delayed versions. It is mathematically possible, but biologically not at all desirable, to center your filters so that these output changes are not in the past, but are brought back up to the present. And the most common way of doing this is with a particular kind of non-causal filtering, zero-phase filtering. Zero-phase filtering filters your data from the past to the present, and then it goes back and starts at the future and goes backwards in time to the first set. And this sounds beautifully and elegant. Zero phase sounds nice and fair. It's the past and the future are all buddy-buddy, and everything sounds wonderful. But it's not, and it's a lot like the problems of an ideal filter, where the way it's described in the name is misleading in terms of its use. If you have any MATLAB code that uses the function filt, which is filt and filt, then this is what it's doing. But they do not remove delay-based artifacts, and actually they double them. So an easy way to see that is what happens when you take our notch filter and apply it to this FM sweep, because this is a nice example of ringing. And you can see that when you apply the regular filter in a causal way, that when that frequency finally occurs, you get ringing after that. When it occurs again, you get ringing after that. The ringing is there, but it only occurs after the signal actually reaches that frequency, so that's fine. It is what it is. If you use, because this has a lot of delay to it, I mean, this is really very extended, persistent in time. That's the kind of thing someone might tell you that filth will take care of, because filth will take these delays and remove the delays. But what it actually does, because it's going backwards in time, is it takes this ringing and it doubles it and puts it over here. It takes this ring, doubles and puts it over here. So what actually happens is that nothing's happening, the ringing starts, then eventually the frequency sweeps through that notch, the ringing continues, it dies off a little bit, it rises again in anticipation of the signal getting that frequency again, and then rings after that. So there's no cancellation here, except in some sense on average. The amount of distortion in the past and the amount of distortion in the future is the same. So there's cancellation in that sense, and that's the sense in which zero phase filters mean no mean cancellation. But it's not getting rid of the problem. It's really making it worse, and it's making it worse in such a way that you start seeing effects before they could possibly ever happen. So this says a lot of what I've already said. It's not just artifacts, but other temporal features. They're also, if you've got some spreading out to the past because you're smoothing things out, what the zero phase filters do is they take that spreading out and they put them also in the future. It does, in some sense, remove this peak delay, but that's not a wonderful thing to do, because you could have just subtracted out the actual measured delay in the first place. And you could have done that in a sentence in your method section, saying that the delay was 10 milliseconds, and so we measured it to be this, but we know it's actually that, without getting this anti-causal rise beforehand. So my pretty strong recommendation is don't use. It causes far more problems than solutions. As with all of these things that I'm saying, it's not that there's never a reason to use it. There are sometimes reasons to use non-causal filters, but you should really know what they're doing and what they're not doing and what you can extract from them reliably and what you can't before you do it. OK, so one of the other topics that I want to talk about was frequency resolution, which is related to windowing. So just going back to the very beginning, the amount of control you have over your spectral analysis. So for instance, in this case, you might be looking at the alpha band, which would be just a few of these, the theta band, which would be just a couple of these. You might want to have much more diversity, more examples of frequencies in those bands. You might want to have a finer frequency resolution than what's given here. If you want that, then you need more time, because this 2 Hertz limit here comes from the fact that you're using only 500 milliseconds. And again, if you want to acquire more data, in this case, acquiring more data means more things happen, then you will get finer frequency resolution. However, in addition to that, it's sometimes you really want, well, no, let me take a step back here. OK, take 2 steps back. So I'm now pulling you out of frequency, and I just want to say something about low passing. We've low pass signals before. Sometimes you want to smear signals, like the 2-point moving average, because that smearing gives you a low pass filter and it cleans up your signal. So when you're smearing information like that, you're really changing your effective time resolution, even though your delta t is the same. You're losing access to things going on in time because of the smearing, but you're doing it deliberately because it's going to help your signal. So you get an effective time resolution that's worse, even though your delta t is the same. All right, now let's go back to frequency. Because time and frequency have this conjugate relationship in the Fourier analysis, sometimes you also want to smear neighboring frequencies, because if you smear neighboring frequencies, that will actually clean things up for you. An example that we'll do is to remove spectral leakage problems. When you do this, then your effective frequency resolution is going to be worse because you're smearing. Even though your delta F has not changed, the way we smear frequencies, which is, I hate to say this because it's going to confuse half the people and it's going to illuminate the other half, but it's like a Fourier version of the low pass. It's like you're taking neighboring frequency bins and averaging them together, and that will accomplish something in the time domain. Or the other way around, you do something in the time domain, and it causes these, this frequency smearing. And the way that it's actually easiest to do this is if you window in the time domain, which just means that you've got your data and you put like a Hamming window or a Hanning window or a Kaiser window, something that is 0 and then goes up to 1 and then goes back down to 0. And it turns out that's a very simple way to change the frequency resolution. All right, so this is the introduction to spectral leakage. And you'll see what I mean in a moment. I want to do a very simple example of what a signal looks like in the time domain. A simple, meaning pure sinusoidal signal, in the time domain looks like in the Fourier domain. So in this case, I have to mention these. The sample time is 10 milliseconds. Our sampling frequency is 200 hertz. That means when we look at this in the Fourier domain, I wish they had come back. We'll have 2 hertz resolution. I have to go back. OK. 2 hertz resolution. Sorry. Delta t. This is wrong. This should be 50 hertz. All right, I have to change my MATLAB. All right, so let me get to the key issue here, which is that, forget about the sample time. Our t is 500 milliseconds long, our duration, which means that our delta f is 2 hertz. So we have 2 hertz resolution. And this particular signal is a cosine at 20 hertz. And so it just pops up here at 20 hertz, no problem. However, when I change the frequency of the sinusoid to 21 hertz, 21 hertz isn't at 20 hertz or 22 hertz. It's not one of our options. And yet, I'm allowed to have the signal and take its Fourier transform. What happens? Well, we might hope that it looks like this. There is no 21 hertz, but we get sum of 20, 22. We split the difference. That's what would be nice to get. We're not allowed to have this at 21 hertz, but we are allowed to have this at 21 hertz. What does it actually look like? It's much, much worse. You do have these two things near each other, but you've got all these other things going on over here also. And they go out pretty far. And if your signals that you're measuring are actually components of some frequencies and others, they can easily get masked by this spectral leakage. Very quickly, what's going on here is because this is sinusoidal, but it's not actually periodic. We've got a plus here and a minus here. It's pretty easy to see what's going on if you allow me to rotate this to move the end. Where's the middle? Here. The end here, and it suddenly jumps up to there. If you rotate a signal in the time domain, it doesn't change the magnitude of the Fourier transform. And so you can see here, it's even more striking. You've got this big, all of a sudden change in your signal. When you have a sudden change in your signal, that's broadband. And so it gives you many, many different frequency components. And so that's ultimately what's the cause of this. So this is a true phenomenon. It's mathematically real. If you take the Fourier transform of this, you get this. There's no two ways about it. But we want to be able to analyze the spectrum and say what's going on here. And so one thing we can do is to smooth or locally smear our frequency bins. We'll do that by windowing. We'll just multiply by a signal that's 0, and then 1, and then 0. and then our new signal will look like this. And you can see how this is actually going to work, because where we had that sudden change from the beginning to the end, where it's not making it periodic, it's now approximately more periodic. We've lost that big sudden change. And when we take the Fourier transform, we see it looks a lot more like what we hoped it would look like in the first place. So this is desirable. You can't control what signals are going into your measurement. There may very well be lots of frequencies there that are not your Fourier frequencies. You have no control over that. So if you're looking at what's going on in the frequency domain specifically, you typically want to be able to do some of this smearing. An easy way and really established way to do this is by windowing. So this is what I just said. It blurs the frequency resolution. What this means, though, is that because you've now lost effective frequency resolution, that if it's appropriate to do windowing, it's appropriate to reduce this spectral leakage, instead of hoping for delta F and then going for a time duration of 1 over delta F, you're really going to need, say, roughly twice that. So you really need even more time than you think you're going to need if you use windowing. Oh, I should have said this up here. Windowing is used whenever you care about the spectrum. And so, for instance, if you're looking at spectral power, if you want to look where the power is in delta versus theta versus alpha, windowing is going to be important there. If you're doing a spectrogram, which looks at the power as it changes as a function of time, spectrograms also use windowing. So there you're always going to get roughly an extra factor of 2 loss in your effective resolution in order to beat down the spectral leakage. And just as an example, if you want 1 Hertz resolution, you probably need 2 seconds. If you want 2 Hertz resolution, you need 4 seconds. No, half Hertz. If you want half Hertz resolution, another typo. This is what I get for adding these last-minute changes on the train. So it's just forget about this. It's reciprocal, but it's reciprocal roughly with a 2 up there instead of a 1. So you really need more time than you thought you needed. Let me see how much time I have left. Oh, that's nice. I have enough time to do this. Envelopes. Envelopes are whenever a signal has some modulations to it. One of the points of an envelope is that it be a slow modulation. For instance, if you've got stuff going on in gamma, 30, 40, 50 hertz, it might be modulated slowly by theta. So theta is much more slow than gamma. 5 hertz is much more slow than 40 hertz. One of the issues with envelopes is that there are no universal definitions. There's no single way to determine the envelope of a signal. All of them agree that it's slow and that it's positive. If an envelope would ever become negative, then it would start multiplying the carrier by a negative number, and it just messes up the whole idea. So we use positive slow envelopes as part of our definition. There are different ways to extract the envelope from a signal, and I'll show you some pictures. The way that's typically used in AM radio is you half-wave rectify the signal and then you low-pass it. The way it's often done with more modern methods in software is you take the analytic signal, which is to say the signal plus I times the Hilbert transform of that signal. In MATLAB, you get the analytic signal entirely by using the Hilbert function. You take the magnitude of that, because it's complex, and you low-pass it. I just want to note that because I'm seeing papers, and some of them I'm the reviewer, and some of them a lot of them I'm just the reader, where people are looking at envelopes and they're not low-passing. And so I just want to, if there's any way to get this out, the low-pass filter is not optional when you do this, because the envelope is any slow amplitude modulation. And just as a very quick example, this is a raw signal, simulated of course, with a high-frequency carrier and a low-frequency modulating envelope. This is the actual envelope. I know that it's actual because I created this in MATLAB. But there's no way to extract this from that. What you do is you use, for instance, the analytic signal's magnitude and low pass it, and you get a very, very nice approximation to it. You might even say that this is as good as that, and certainly if the brain is doing this stuff, the brain isn't doing Hilbert's or half-wave rectification, it's doing whatever it does, but it can still extract an envelope. If you don't low pass it, you get all of these high frequency stuff, and it can get much, much worse even than that. So if you're taking an envelope, please low pass after you take the envelope. All right, so I've managed to actually finish everything, only a minute or so late. And let me give my very brief conclusions, which are that signal processing is complicated, but it's not too complicated. And all of the stuff that you've been doing in your lab for the last few years is probably fine, but you may want to change some of it. And you may actually want to change some of it to make your data analysis better. Intuition is great, and that's what we use all the time. The mathematics will always win if there's an argument between your intuition and the mathematics. However, if we can guide your intuition to be stronger, more educated, better in tune with the mathematics, then your intuition will always be faster than using the mathematics. And so I always recommend going with that. And that's all. Thank you.